Laplace transform is one of the most important transforms that is used in engineering, control systems, signal processing, and it has a very close relationship with Fourier transform, and Fourier transform is commonly used in all sorts of applications in engineering, medicine, physics, and signal processing, and so forth. So, with derivatives and differential equations, Laplace transforms do help us in simplifying the problem and getting to a solution to a differential equation, specifically an initial value problem, easily if we can have a Laplace transform. So, Laplace transform, by definition, it is an integral transform. And we all know what a transform means. We move from one domain to another domain. So it's like a mapping between, say, the domain T to the domain standard notation S. So we have f of t, that becomes f of s. And there are some operational properties that Laplace transform provides. Typically, any transformation would transform a function to a different domain where things are going to be easier to handle compared to simply directly using f of t, which is what I meant by an initial value problem. Handling an initial value problem over here might be difficult, but if you transform it and get over there, it might be easier. So it is a great utility to have. So the definition of Laplace transform is very straightforward. So the Laplace transform of the function f of t, we can denote it by f of s. In control systems, it would be h of s. And you take a function f of t, which is in one domain, and we move it to another domain, which is s. And the definition is just f of t e raised minus st dt. With Fourier transforms, we have a bidirectional transform where we go from negative infinity all the way up to positive infinity. But Laplace transforms, we simply define it from 0 to infinity. Depending on what function we use here, g of t, then we write it as uppercase g of s. H of t, we write it as uppercase h of s, and so forth. And one of the conditions for this to exist the integral has to converge, and if it doesn't converge, then a Laplace transform will not exist. Converge in the sense it has to approach a constant value and it can't just blow up. So I'm going to start with a very simple example. Find Laplace transform of 2. So here f of t is equal to 2. which I could write it as integral 0 to infinity 2 e raised minus st dt. I could pull 2 out. I'm integrating with respect to t, so I would have e raised minus st over minus s, 0 to infinity. Upper limit would make the exponential 0, so 0 over minus s. Lower limit, I'd have minus of minus 1 over s. E raised 0 is 1, so the answer is 2 over s. In a similar manner, if we want to find the Laplace transform of t, that would mean f of t is simply t. L of t would be integral 0 to infinity t e raised minus st dt. If we use integration by parts, we would have t e raised minus st over minus s plus e raised minus st over s. And the limits would be from 0 all the way up to infinity. Of course, the upper limit, it's going to become 0, and the lower limit would be e raised minus s times 0, which is 1. So upper limit would simply be 0, and the lower limit, I feel like I missed something here. It's s squared. Would be 1 over s squared with a positive. It should be minus. So we have 1 over s squared. And you can see that we moved from a domain t, so the function was t. The resulting answer is 1 over s squared. We had 2, and we moved to 2 over s. So this would be f of s, and that would be f of s. So we don't have to find the Laplace transform for each and every single function that we encounter. Rather, we have a set of functions that we know, and we extend that idea to other functions using trigonometric identities or, properties of exponentials, logarithms, and so forth. So as the general rule of thumb, the Laplace transform of a constant k is simply k over s. Laplace transform of t raised n, it has to be a function of t, and that would be equal to n factorial over s raised n plus 1. N has to be integer powers, so 1, 2, 3, ... keep on going. Laplace transform of e raised at is equal to 1 over s minus a. Laplace transform of sine k times t is k over s squared plus k squared. Laplace transform of cosine k times t is s over s squared plus k squared. Laplace transform of sine h hyperbolic sine kt is k over s squared minus k squared. Laplace transform of cosine h kt is s over s squared minus k squared. One of the properties to note is the Laplace transform of f of t plus g of t is equal to, or plus or minus, Laplace transform of f of t plus or minus Laplace transform of g of t. So you can distribute the Laplace transform, and also Laplace transform of a constant k multiplied by a function is simply equal to k times the Laplace transform of the function. And we can also find the Laplace transform of piecewise continuous functions. There is some theory behind it, but we don't need that here, so I'm going to just skip that. So if we do some integration, if we integrate e raised at and we did Laplace transform, we would get 1 over s minus a, and perhaps I can show you that. So Laplace transform of e raised at is integral 0 to infinity e raised at multiplied by e raised minus st dt, which would be equal to integral 0 to infinity e raised minus s minus a t dt. If I integrate it, I would have minus 1 over s minus a e raised minus s minus a t evaluated between 0 and infinity. I plug in the upper limit, it is going to become 0. Lower limit, minus of minus 1 over s minus a, e raised 0 is 1, so we end up getting 1 over s minus a. So we can integrate this in a similar manner for sines and cosines. Sine kt, you could write it in terms of e raised minus st and e raised plus d, plus st, and you can integrate it and you'd end up getting k over s squared plus k squared and so forth. So here is our first example on Laplace transform of f of t. So the function is defined piecewise. You have to keep in mind Laplace transform of f of t exists for a piecewise continuous function as long as the integral converges on the interval. Oh, the book uses square brackets, or set brackets. Doesn't matter. So the Laplace transform of f of t would equal to integral 0 to infinity f of t e raised minus st dt. I could split the integral here from 0 to 1 f of t e raised minus st dt plus integral 1 to infinity f of t e raised minus st dt. Now we could use a standard Laplace transform provided the limit is from 0 to infinity, but that is not the case here. So we have 0 to 1, minus 1 e raised minus st dt plus integral 1 to infinity plus 1 e raised minus st dt. That would equal to e raised minus st over s, evaluated between 0 and 1, e raised minus t over minus s, evaluated between 0 and 1. Plug in the upper limit, we have e raised minus s over s, lower limit minus 1 over s, upper limit minus e raised minus st over minus s, lower limit minus of minus 1 over s. That's strange. I must have made a mistake somewhere here. Oh, the limits. It's 1 to infinity. So, upper limit we have 0 minus the lower limit minus e raised minus s over minus s. So that would become 0. We have e raised minus s minus e raised minus s over minus s, 2 e raised minus s over s, minus 1 over s. And s has to be greater than 0. Here is another piecewise defined function, and we want to find the Laplace transform. So integral 0 to infinity f of t e raised minus st dt. Split it up at the end point 0 to 1. F of t e raised minus st dt plus integral 1 to infinity f of t e raised minus st dt. Integral 0 to 1 2t plus 1 e raised minus st dt plus the second integral is 0 because the second piece is 0. Integral 0 to 1 2t e raised minus st dt plus integral 0 to 1 e raised minus st dt. Now, we don't have to integrate this entirely. Why? If I pull the t out, I have t raised 1 e raised minus st dt. And here I have 0 to 1. I could write this as 1 times e raised minus st dt. Well, we do have to integrate because our limits are different. It's not infinity. So 2 times t e raised minus st over minus s plus e raised minus st over s squared. And for that term, we have minus e raised minus st over s. Evaluate it between t equals 0 and t equals 1. That is due to integration by parts. Upper limit, I have e raised minus s over minus s plus e raised minus s over s squared minus e raised minus s over s. Lower limit minus 0, 1 over s squared minus 1 over s. So we have 2 minus 2 e raised minus s over s plus e raised minus s over s squared minus 1 over s squared plus 1 over s. Which is 2 over s squared minus 2 s e raised minus s plus e raised minus s minus 1 plus s, and that would be it. Think integration by parts, that should be a negative. So negative e raised minus st so if you want to avoid mistakes, don't do it in your head, just write it out. Here is a piecewise defined function, and we have to find the Laplace transform of this piecewise defined function. It is easy to note that f of t is 0 for t less than or equal to 1, and the other bit is a line, and if you can't recognize what that line is right away, we could use the point slope form. So if I call that y and I'll call it t1 and y1. Y minus 2 be equal to t minus 2. The slope here is 2 minus 0 divided by 1 minus 0, which is 2. So we end up having f of t equals 2t minus 4 plus 2. We get 2t minus 2. So for t greater than 1, the function that we have is 2t minus 2. Now we could find the Laplace transform like we always do. Integral 0 to 1 f of t e raised minus st dt plus integral 1 to infinity f of t e raised minus st dt. The first piece would become 0. The second piece we have 2t minus 1 e raised minus st dt. Actually 2t minus 2, so we could pull 2 out, 1 to infinity t minus 1 e raised minus st dt. So integration by parts would give us t minus 1 e raised minus st over minus s minus e raised minus st over s squared. T equals 1 to t equals infinity. When we plug in the upper limit, both of those terms would become 0. So the lower limit, we have minus 2. And the first term would become 0 because 1 minus 1 would be 0. Minus 1 over s squared. which gives us 2 over s squared. So here is another function where we have an interval over which the function is defined. So f of t is 0 for 0 less than or equal to t less than or equal to a. It is equal to c for a less than t less than or equal to b, and 0 for t greater than b. So all we care about is whether the function is continuous on an interval, which it is in this case. The function is continuous between a and b. So the Laplace transform here would be equal to integral 0 to infinity f of t e raised minus st dt, which would be equal to integral 0 to a f of t e raised minus st dt plus integral a to b f of t e raised minus st dt plus integral b to c f of t e raised minus st dt. Not b to c, rather it is b to infinity. On the interval 0 to a, f of t is 0, so that becomes 0. Integral a to b, it is simply a constant, e raised minus st dt, and it is 0. So we have a to b, c e raised minus st dt. Common mistake, you may say, oh, I have a constant, so I could simply use one of the standard formulas that I have for Laplace transforms and plug it in here and call the answer as c over s. But we can't do that because that only applies if the interval is between 0 and infinity, and that is not the case. Here we have a to b. So when we integrate, we have c times e raised minus st divided by minus s a to b. We plug in the upper limit, e raised minus bt over minus s, lower limit, e raised minus at over s. We have s as a constant, so we end up having e raised minus at minus e raised minus bt times c divided by s. It's not t, I'm sorry, it's s. So you cannot have t in your answer because we are changing the domain. So we go from the t domain to the s domain, so the answer cannot have a t. So even though I recognized my mistake right away, because I know that when we transform, the resulting answer has to be a function of s and not a function of t. So here we have another function where we want to find the Laplace transform of e raised minus 2t minus 5. So integral 0 to infinity e raised minus 2t minus 5 times integral minus st dt. Integral 0 to infinity e raised minus 2t times e raised minus 5 e raised minus st dt. I could pull e raised minus 5 out of the integral because it is a constant. And we will simply have e raised minus 5, e raised minus 2t times e raised minus st dt. And we know the Laplace transform of e raised at is 1 over s minus a. And what we have here as an integral is a proper Laplace transform in the sense it is defined on the required domain. So Laplace transform of the given function would be equal to 1 over e raised 5 times 1 over s minus 2. So we have 1 over e raised 5 times s plus 2. So here we have to find the Laplace transform of t squared times e raised minus 2t. So that would simply equal to integral 0 to infinity t squared e raised minus s plus 2 t dt. As an operator, s plus 2, I could write it as s star, as s plus 2. Which would simply mean 0 to infinity t squared e raised minus s star t. But that is Laplace transform, t squared times e raised minus s, whatever variable that we have. So if we use the transform, we'd simply get Laplace transform of t raised n is n factorial divided by t raised n plus 1. Excuse me. S raised n plus 1, where n is equal to 1, 2, 3, and so forth. So, using the same idea, n in the integral is 2. So what we have is 2 factorial divided by s star raised 2 plus 1, which should be 2 divided by s star cubed. But what is s star? S star is simply a translated version of s, and in this case it is s plus 2. So the answer is 2 over s plus 2 cubed. So before we move on, it is always good practice to specify an interval where the transform would exist. Here, s has to be greater than negative 2, because if we plug in negative 2, it is going to become infinity, and the Laplace transform is a continuous transform. So in that example, we wanted to have x to be greater than negative 2, and same here for it to exist. So here we want to find the Laplace transform of t sine t. Well, integration by parts is an option in this problem. I would not recommend it because it's going to take forever and you're about to go in circles. So how do we go about doing this without using integration by parts? Recall sine t can be written as e raised it minus e raised minus it divided by 2I. You may ask me, well, where is this coming from? We've used this multiple times. Euler's formula. So what I'm going to do integral 0 to infinity t multiplied by e raised it minus e raised minus it divided by 2I times e raised minus st dt. 2I is a constant, so I'm going to pull that out. 0 to infinity t e raised it times e raised minus st. T e raised minus it e raised minus st dt. I could split the integrals 1 over 2I. Integral 0 to infinity t e raised it times e raised minus st dt minus integral 0 to infinity t e raised minus it times e raised minus st dt. So that would be 1 over 2I integral 0 to infinity t e raised minus s minus I t dt minus integral 0 to infinity t e raised minus s plus I t dt. Now, I could say let S1 is equal to S minus I and S2 equal to S plus I. Integral 0 to infinity t e raised minus S1t dt minus integral 0 to infinity t e raised minus S2t dt. But both of those are Laplace transforms in and of themselves. So we know the Laplace transform of t. Recall t raised n is n factorial divided by s raised n plus 1. So I could rewrite the first one as 1 factorial divided by s1 raised n plus 1, which is 2, minus 1 factorial divided by s2 raised 2, now I will have 1 over 2I, 1 over s1 squared minus 1 over s2 squared, which would give me 1 over 2I, s2 squared minus s1 squared over s1 squared, s2 squared. So s2 squared minus s1 squared is s plus I squared minus s minus I squared, which is s squared plus I squared plus 2is minus s squared plus I squared minus 2is, which would give us x squared plus I squared plus 2is minus s squared minus I squared plus 2is. Those would get cancelled and we would simply have 4is. In the denominator, we have s1 squared, s2 squared, so s minus I squared times s plus I squared, s squared plus I squared minus 2is, s squared plus I squared plus 2is. I squared is minus 1, so s squared minus 1 minus 2is, s squared minus 1 plus 2is, s raised 4 plus 2is cubed minus s squared minus 1 minus 2is minus 2is cubed plus 2is minus 4i squared s squared. So those two will get cancelled. Those two will get cancelled. What we have here is s raised 4. Looks like I'm missing an s squared term. I think that has to be s squared. Yes. Let me just redo this. I went one step ahead. S raised 4 minus s squared 2is cubed minus s squared plus 1 minus 2is minus 2is cubed plus 2is minus 4i squared s squared. Those two would go away. Those two would go away. S raised 4 minus 2i squared plus 1 minus 4 s squared and plus 1. So you'd end up getting s squared plus 2s squared plus 1, which is simply s squared plus 1 squared. So the numerator is 4is, denominator is s squared plus 1 squared. Plug it in. So the Laplace transform of t sine t would be 1 over 2i times 4is divided by s squared plus 1 squared, which would give us 2s divided by s squared plus 1 squared. Here is another problem which uses exponents and cosine terms. So the Laplace transform of e raised t cosine t is simply the integral 0 to infinity e raised t cosine t e raised minus st dt, which I could write it as integral 0 to infinity cosine t e raised minus s minus 1 t dt. But recall Euler's formula, cosine t is simply e raised it plus e raised minus it divided by 2. So I could plug that in here, e raised it plus e raised minus it divided by 2, multiplied by e raised minus s minus 1t dt. I could pull the 1/2 out, integral 0 to infinity, e raised it plus e raised minus it times e raised minus s minus 1t dt. I can split the integrals and write it as 1/2 integral 0 to infinity e raised it minus s minus 1t dt, and likewise e raised minus it e raised minus s minus 1t dt. So I've got to do a bit of algebra here. I'm going to keep the e raised minus st as is, and do the same thing over here before I rearrange things. 0 to infinity, e raised minus it, e raised t, e raised minus st dt. 1/2 integral 0 to infinity, e raised t, e raised minus s minus I t dt, plus integral 0 to infinity, e raised t, e raised minus s plus I t dt. Now let s1 equals s minus I and s2 equals s plus I. Then this is a linear translation, so we have 1/2 integral 0 to infinity, e raised t, e raised minus s1t dt, integral 0 to infinity, e raised t, e raised minus s2t dt. Both of them are exponentials, they are Laplace transforms themselves, and we know that Laplace transform of e raised t is 1 over s minus 1. So we would have 1/2 1 over s1 minus 1 plus 1 over s2 minus 1. So Laplace transform of e raised t cosine t would equal 1/2 s2 minus 1 plus s1 minus 1 divided by s1 minus 1 times s2 minus 1. So the numerator, s2 minus 1 plus s1 minus 1, would equal to s1 is s minus I, s2 is s plus I, so s plus I minus 1, s minus I minus 1, the i's go away. We have 2s minus 2, we'll get 2 times s minus 1. The denominator, we have s minus 1 times s1 minus 1 minus or times s2 minus 1, which is s1 s2 minus s1 minus s2 plus 1. s1 s2 is s plus I times s minus I minus s minus I minus s plus I plus 1. The first term simply becomes s squared minus I squared minus s plus I minus s minus I plus 1, which gives us s squared minus 1 times the minus outside. The s's go away. No, they don't. Minus s minus 2s. The i's go away. Plus 1. we'd end up having s squared minus 2s plus 2. So the numerator is 2 times s minus 1 divided by 2 times s squared minus 2s plus 2. So we have s minus 1 over s squared minus 2s plus 2. Here we have to find the Laplace transform of f of t is equal to minus 4t squared plus 16t plus 9. This is pretty straightforward. You've got to keep in mind that we don't have to integrate it each and every time. If it is a standard form, we simply use the standard form and we find the Laplace transform. Splitting the integrals, so minus 4 integral t squared e raised minus st dt plus 16 integral t e raised minus st dt. And it is just a constant, 9 integral e raised minus st dt. And the limits are 0 to infinity. Keep in mind, you could use Laplace transform only if the limits are from 0 to infinity. So every single integral is a standard Laplace transform. So n here is 2, and there is 1, and there is 0. So we have minus 4 divided by, or 2 factorial divided by s raised 2 plus 1, plus 16 times 1 factorial divided by s raised 1 plus 1, plus 9 times 0 factorial divided by s raised 0 plus 1. So we have minus 8 over s cubed plus 16 over s squared plus 9 over s. So here we have 2t minus 1 cubed. So we could FOIL this and write it as 2t minus 1 times 2t minus 1 squared, which would be 2t minus 1, 4t squared, minus 4t plus 1, which would be 8t cubed minus 8t squared plus 2t minus 4t squared plus 4t minus 1. And that would be 8t cubed minus 12t squared plus 6t minus 1, which I could simply write it as 8 Laplace transform of t cubed minus 12 Laplace transform of t squared plus 6 transform of t and Laplace transform of 1. That would give us 8 times 3 factorial divided by s raised 3 plus 1, 12 times 2 factorial divided by s raised 2 plus 1, 6 times 1 factorial divided by s raised 1 plus 1 minus 1 over s. So we would have 48 over s raised 4 minus 24 over s cubed plus 6 over s squared minus 1 over s. So here we want to find the Laplace transform of 4t squared minus 5 times sine 3t. So I could write this as Laplace transform of 4t squared minus Laplace transform of 5 sine 3t. Keep in mind I could only do this if I have addition or subtraction. I can't do it if I have division or multiplication. So that would equal to 4 times the Laplace transform of t squared minus 5 times the Laplace transform of sine 3t. The Laplace transform of t squared is 4 times 2 factorial divided by s raised 2 plus 1, because the power here is 2, minus 5. We know the Laplace transform of sine kt it's k over s squared plus k squared. So we would have 5 times 3 over s squared plus 3 squared. So we have 8 over s cubed minus 15 over s squared plus 9. So here we have an exponential and a hyperbolic function. Now we can't directly distribute the Laplace transform like we did in the previous problem here because we have multiplication. So the Laplace transform of e raised minus t cosine ht would be equal to integral 0 to infinity e raised minus t cosine ht e raised minus st and dt. So what I can do is 0 to infinity cosine ht e raised minus s plus 1 t dt. I'll call s plus 1 as s star. And I'd simply have 0 to infinity cosine ht e raised minus s star t dt. That is the Laplace transform of cosine h of t. And we know what that answer is. It is simply s star divided by s star minus k squared. K in this case is simply 1. If I plug s star back in, I'd have s plus 1 over s plus 1 squared minus 1. That would be s plus 1 over s squared plus 2s, s plus 1 over s times s plus 2. Now that is one way of doing the problem. What is another way if there is one? Recall cosine ht is simply e raised t plus e raised minus t divided by 2, which would mean I would have Laplace transform of 1 over 2 times 1 plus e raised minus 2t. It's 1 over 2 Laplace transform of 1 plus e raised minus 2t. Oh, sorry, minus 2 times t. So that'll be 1/2 Laplace transform of 1 plus Laplace transform of e raised minus 2t. We know Laplace transform of 1 is 1 over s. Laplace transform of e raised minus 2t is 1 over s plus 2. Did I make a mistake here as I sped through? Minus s plus 1t minus s star minus 1. Oh. Expecting a minus somewhere in the middle here. Never mind. So 1 over 2, I'll have s plus 2 over s plus s over s plus 2, which should be 1/2 2s plus 2 over s times s plus 2. We have a 2 in common in the numerator, so 2 times s plus 1 divided by 2, s times s plus 2. 2's would go away. So the answer is s plus 1 over s times s plus 2. So you could either take the approach that's above, or you can take the approach that is below. It's just a matter of preference. It's entirely up to you. So here we have cosine squared t. Now, anytime we have a power of t, we've got to use an identity, a trigonometric identity. So we know cosine squared t minus sine squared t is cosine 2t. So I could rewrite sine squared t as 1 minus cosine squared t. So 2 cosine squared t minus 1 would equal to cosine 2t, which would imply cosine squared t is cosine 2t plus 1 divided by 2. So Laplace transform of cosine squared t is equal to the Laplace transform of cosine 2t plus 1 over 2, which is equal to 1 over 2 Laplace transform of cosine 2t plus the Laplace transform of 1/2. Laplace transform of cosine 2t is simply s over s squared plus 2 squared, because k is 2. The Laplace transform, I pulled the 2 out, so this has to be just 1. The Laplace transform of 1 is 1 over s. So we have 1 over 2 s over s squared plus 4 plus 1 over s. Unless you think that things are going to simplify, there is no need for simplification. Perhaps I could combine these two fractions in this problem. I could write it as s squared plus s squared plus 4 divided by s times s squared plus 4. which would give us 1/2 2s squared plus 4 over s times s squared plus 4. We have a 2 in common in the numerator. So if I pull that out, the 2's will get cancelled, and we have s squared plus 2 divided by s times s squared plus 4. And you can see that I did not even put the integral symbol. I simply used the operator L, and I just went with it with the standard identities. But you can only do this if we don't have a piecewise function or something that is not defined on 0 to infinity, one of those. So here we have 10 cosine t minus pi over 6. Couple of ways to do this problem, and I'll show you both approaches. Let's see, could we do it that way? Well, it might actually be harder. So what we can do is we'll do it this way. Cosine a minus b is cosine a cosine b plus sine a sine b. So here a is t and b is pi over 6. So we get cosine t cosine pi over 6 plus sine t sine pi over 6. Cosine t cosine pi over 6 is simply cosine 30. Cosine 30 degrees is square root of 3 over 2. And sine 30 is simply 1/2. So Laplace transform of 10 times cosine t minus pi over 6 is equal to 10 times the Laplace transform of cosine t minus pi over 6, which would be equal to 10 times the Laplace transform of cosine t square root of 3 over 2 plus sine t times 1/2. 10 times Laplace transform of cosine t square root of 3 over 2 plus the Laplace transform of sine t 1 over 2 times square root of 3 over 2 times the Laplace transform of cosine t 1 over 2 times the Laplace transform of sine t. So the Laplace transform of cosine t is simply s over s squared plus 1 squared. Sine t is 1 over s squared plus 1 squared, because k here is 1. We have a 2 in common, so we could pull that out. 10 over 2 square root of 3s over s squared plus 1 over s squared plus 1, which would give us 5 times square root of 3s plus 1 divided by the common denominator s squared plus 1. So if you have addition, terms in addition or subtraction, and regular functions, then you can simply apply the Laplace operator like the way I did over here, without the need for using integrals like that problem or the problems prior to that, such as that one where we used integrals frequently. But if you simply have things in addition, you can use the Laplace operator, which is L, and get the answer directly without even using the integral sign.